Hi everyone, and thank you so much for joining today for iStructE Essays Technical Talk number 6 for the year. I'd like to give a warm welcome to Peter Debney, who will be speaking to us today on computational engineering. Who better to be providing this talk than Peter Debney, author of the recently published iStructE Guide on Computational Engineering. In addition to working as a civil engineer, Peter has worked directly in the engineering software industry, helping develop the CAD programs XSteel for Tekla Structure and 3D Plus, as well as the Finite Element Analysis and Design program GSA. Without further ado, I'll hand over to Peter Debney. Thank you so much.
Okay, so thank you, Fiona. Yes, thank you. Thank you for the introduction. Yeah, I'm Peter Debney. I wrote Computational Engineering. So today we're going to have an exploration of the book, how I came to write it, and I think more importantly, what it contains. So yeah, me, introduction to me, personally speaking, I've always loved making models, Lego, Airfix, discovered computers as a teenager. I don't know how many people remember these particular computers, but these were the first ones that I played with and often broke, but we won't go into that. And because I love buildings, not just Lego ones, I then went to University of Surrey, studied civil engineering, and then I've worked at a variety of companies, initially as a structural engineer with a specialism in computing, and then in computing with a specialism in structural engineering. I joined Arup 20 years ago this year, and joined the Oasis group, which is over Arup Systems at Arup Software, about 16 years ago. Working mostly in the structural, but these days also run the support team, the quality management system, and so on. Okay, all right. So the book itself, as I really wanted a book that was. I wanted a book that explained the broad sweeps of computing for structural engineers, sort of equivalent to J. Gordon's Structures or Why Things That Don't Fall Down. Yeah, and if you haven't read that book, read it. It's absolutely brilliant. Love it. It got me through my degree, that one. Anyway, so I wanted the book that explained what and why of computing for engineering, not just a list of formulas. So I did put some useful ones in the back, and because that book didn't exist, I realised that I was going to have to write it. So it encompasses about 35 years of experience in engineering and computing, mostly aimed at graduates, but it's also been picked up by a lot of senior engineers wanting to deepen their knowledge, and also by some of those more senior still wanting to know what the youngsters are talking about. Now, most engineering books are like car manuals that tell you how the engine works, and once you know the mechanics, you're then expected to take the keys and drive off. Whereas computational engineering is more of a driver's manual, explaining what you need to know as a practicing engineer. And so it covers why we use computers when designing, but also design methodologies as well. It touches on parametrics, quite a large section on finite element analysis. It goes into optimization of structures, and then finishes with a look into the future of structural engineering, artificial intelligence, machine learning, digital fabrication, cloud, quantum, and some thoughts on the future role of engineers. And there's some appendices as well, with some useful bits and pieces. So why use computers to do engineering? Well, the main reason is because they are very, very good at doing maths, far faster than we can. They'll do that without error, if programmed correctly, without tiring, apart from possibly overheating, and without getting bored of mind-numbing tasks. Because despite names like artificial intelligence, they actually have no minds whatsoever. They just get on with it. Computers can do our drudge work, freeing us up to do all the interesting things. The creative, the imaginative, the interpreting, the communicating, and the human. So design, first of all. So one of my personal bugbears is the confusion over the dual meaning of the word design. One One meaning, understanding and interpreting the client's brief and needs, working with the architects and other consultants to determine the best approach, the form, the layout, and the methodology to meet those needs, or calculating the beam sizes and rebar quantities. Now, option 1 is creative. Number 2 is mechanical. Though still crucial. The devil is in the detail, and we must never forget things like the Hyatt Regency Hotel. So now, I know some people specialize in the details, and we love you, that they are very important, and you guys always impress me with the depth of knowledge, and we need that knowledge to keep it safe. On the other hand, in the book, I'm looking at the scheme rather than the detail aspect of design. So how do we go about designing? Well, not on a blank sheet of paper like this, but with requirements, constraints, and options. Now, the requirements and constraints speak for themselves, but the options, I think they're the interesting part. So every year in the iStructE chartership examiners complain that candidates struggle to find two distinct solutions to exam problems. We know the options. Any scheme, we know the options. It's a brace steel frame or a moment concrete frame. Well, maybe not. I mean, certainly the students I've taught at local universities know that two options are always a truss or a portal frame, which is a similar problem itself. But in engineering, we talk about creativity, not enough in my opinion, but it's in the options that creativity is most found. And it's said that if all you have is a hammer, all problems look like a nail. Now, when I was preparing for my chartership exam more years ago than I'll care to mention at the moment, I decided to create an exhaustive list of all the possible ways of creating or crossing a horizontal gap, and likewise to keep a load at height. I mean, I never did finish because there were far too many options, possibly an infinite number, but certainly a very large number. There is no excuse for just two options. So for me, creativity comes from knowing what options there are and then choosing the best options. Now, how we go about implementing that. So Hermann von Helmholtz and Henry Poincaré put it more succinctly. So creativity comes from saturation, learning everything, especially about the subject, but also everything else. As engineers, we can learn so much from natural structures such as skeletons and muscles, shells and trees. We can learn from art, from maths and science, from everything. Then there's the incubation, thinking about the problem, sleeping on it. This part can take time. There's illumination. You get an idea. Now, Murray Gell-Mann got his Nobel-winning quantum breakthrough by making a mistake in a lecture. But without the saturation and incubation periods, he would never have realized the error was the answer he was looking for. And then finally, validation. You have your scheme, your approximate sizes, but you now need to do the analysis and details to ensure that it will work, as well as exploring how to make it better. Okay. Now, the Design Council puts design another way. See earlier about there being more than one way to do something, and they introduced us with the design double diamond, where the project you start from the left and work away across the right. And you note that in the discovery and development phases, the design broadens when you explore the options, what they can be. So don't close these options down too soon. Whereas it's in the define and delivery phases that you need to refine and concentrate what the problem is and what is your solution. And even this doesn't take into account the cyclical nature of design. So to help with that, I want to take a little closer look at the development phase and the method we call parametric design. Now, we all know that layouts are driven by constraints, dimensions. We know it too well when the architect or client changes them, making the scheme bigger or smaller and so on, and then we have to start all over again. And with parametric design, we plan for the change by encapsulating those constraints and rules into a geometric computer model, which is a design led by parameters. And this might be mundane things like the span of a decking slab, or it might be complex like the offset from a curved spline surface. Parametric design started in the aeronautical industry, and I think the first significant parametric design in the building industry was Frank Gehry's Guggenheim Museum in Bilbao, in Spain, which opened back in 1997. Now, parametric design in the 90s was on supercomputers running software design for making fighter jets. Today, it's much simpler programs like Rhino, you see here, running a plate of spaghetti script in Grasshopper to generate the geometry, and then exporting the FE analysis, export to FE for analysis and CAD for detailing and documentation. Now, BIM, building information modeling, used to be all about neutral file formats, but where today we've moved on. Now it's all about digital workflows, though the underlying principle of data reuse remains the same. Now, you've got design, you need to validate the design, usually using finite element analysis. Now, FE was first used in the 1950s, aircraft again, and in the 1960s on buildings. Now, as far as I know, the first structural engineering use was by Arup on the Sydney Opera House, though I'll be very interested to know if you know of any earlier examples. FE books, as you know, they tend to focus on the maths of the methods, which is great if you want to write your own program, but the majority of engineers just want to use a commercial program. So my aim here was to teach how to make the best models with a little bit of maths thrown in, as it can be interesting and can be informative. And as a side, I think FE universities, FE the maths tend to be taught more at universities because marking maths is a lot easier than modelling. Modelling is an art, and therefore there is no one right way of doing it. Rather, better ways and worse ways, on an occasionally completely wrong way of doing it, of course. So, what is a model? Yeah, models are not reality. So this is not a real beam. These are not real connections. They are a simplified representation of reality. So the model doesn't represent everything about the real connection, the real beam, but they are close enough for engineering. So the model is a simplification of reality, it's not reality, and therefore it's important to remember that all models are wrong, but some models are useful. Yeah. Is it possible to do a totally realistic model and test it with everything the real structural experience over its service life? No. The closest you can get is to build the structure for real out of steel and concrete, then load it until it breaks, then repeat with other loadings. But would that be 100% accurate? Well, no, that won't be either. Due to tolerances, the steel and concrete sections will be slightly different size. The frame won't be quite as plumb. The wind, snow, and earthquake loads will not be exactly the same. Besides which, we don't know exactly what the structure will experience over the next 50 years. It's just not possible. As I said, the art of engineering is to get answers which are close enough. To illustrate this, let's consider the stool paradox. Now, if you sit centrally on a three-legged stool, then your weight will be carried, approximately, equally down each leg. Design load on each leg is your weight divided by 3. But if you sit on a four-legged stool, then will design load be divided by 4? No, because the stool will not be perfectly built, the floor it sits on won't be perfectly flat, and only 2, possibly 3 legs will actually be fully in contact with the floor. Your weight will be mostly carried by 2 of the legs, meaning that design load is now your weight divided by 2, an increase of 50% thanks to the addition of an extra leg. Now, when we build analysis models, we tend to assume the structure will be perfect, the floor is smooth, the stool is even, every leg is fully in contact with the floor. Reality is not so neat. On the other hand, structures will often work the way we design them, so if they have enough ductility. In the case of the stool, the connections may have a little bit of flexibility if they're not glued, the top may warp a bit, and so on. Now, our building structures often have similar problems. University, we tend to study statically determinate structures, so pin supports are fine. If a footing moves, they make very little difference to the structure. We have an indeterminate structure, multi-span beam, a frame, a raft, then suddenly the support stiffness becomes crucial and you can get rubbish results like I'm showing here. Interesting enough, this was a reproduction of a mistake that I did make myself many years ago. So some moment redistribution occurs because of plasticity, but a lot will occur not because of the error in assuming that support is infinitely stiff. Model the ground with springs, or support with springs, and you'll notice the sagging increases, hogging reduces, and so on. And likewise, the retaining wall model I did back there would also give correct bending moments in the base. Now, do we really know how stiff the beam will be? How stiff the ground? Approximately. How confident can we be with the results? Well, take a steel beam. When rolled to European tolerance standards, I'm sure South African standards are similar, its area can vary by about 4% and its bending stiffness by about 10%. This means that every factory-made beam, there is no point calculating deflections beyond two significant places, or two single figures. Concrete beam stiffnesses will vary even more, both from the tolerances, effects of cracking, and so on. Now, FE models are analogues of the real structure. And we model them with 1D, 2D, and sometimes 3D elements. Now, 1D elements are great when the stress flows are essentially one-dimensional, like in beams. The one dimension, the length, is considerably more than the other two. 2D elements are suitable when the stresses move in two directions. One dimension, thickness, being considerably less than the other two. And 3D elements, well, I mean, guess about that. And now, these are all analogies, and these analogies will break down when the stress flow directions change, like the connections between the beam or slab and the column. And for this reason, there's an simple overall model can inform a more detailed model of a part of the structure, but you would not want to model the entire structure in such detail. I mean, you would not want to model either of these two examples totally in 3D elements. It would be a complete waste of time. So what does make a good model? It needs to be as accurate as necessary. Do a sensitivity check, vary the stiffnesses, the dimensions, do a p-delta or a nonlinear analysis. Are the results close enough? It needs to be as realistic as appropriate. Remember that increased realism is subject to diminishing returns. Stop when it's not worth continuing. It needs to be as simple as possible. Simplicity, this comes from experience. I mean, my first FE model back in university took 24 hours to run on the university mainframe. Today, I would achieve the same results with perhaps a model with perhaps maybe only 1% of the number of elements in. It also needs to be useful and relevant. Does the model give you the answers you need? For example, static or dynamic analyses often require quite different models. So the essential question you need to ask yourself is, what is the question that I am trying to answer? Then make sure that you design your model to achieve that. Now, analysis methods. Now, it would not be a book looking at FE if it did not have some exploration of the maths behind the methods. Now, my requirement in the book was to do it with a minimum amount of maths. And now we've only got, let's say, 5 minutes to look at the topic, which normally takes up entire textbooks. So let's see if I can keep it both useful and simple. Now, it's a simple beam. We know that when we apply a force to a structure, its deformation, U, is proportional to the external force, F, and inversely to the stiffness, or stiffness times deflection equals force. If you look at this beam element, which only has axial stiffness, keep it simple, you'll know it has some stiffness horizontally in the x direction, but 0 in the y direction. Now, there can be forces there will be forces applied to both ends of the element, which can cause both ends to move. Again, keeping it simple and looking only at the forces and displacements in line with the elements, we can see there's U1, U2, N1, N2, and so on. And we can write these equations out in a matrix form, so that we can then use matrix maths to find all the displacements and all the forces. Now, we already know some of the forces. These are the externally applied forces. The other forces we're finding are the reactions. And also you find when you do the analysis, the forces within the structure all cancel out because it's in equilibrium, or at least close enough. So we have the stiffness of each individual element, or each element stiffness matrices, and we combine these together to make a global stiffness matrix. And for simplicity, I've shown them separately, but in reality they'll actually overlap and combine wherever they have a shared nose. And for extra simplicity, we can write this as Ku equals F. So the stiffness matrix K times the displacement vector U equals the force vector F. Now, we need to find the displacements U, and but we can't divide by a matrix. Instead, we need to multiply by the inverse of the stiffness matrix. Well, on both sides, and now I'm not going to tell you how to invert the matrix, and besides, it's not important. But what we then get is the nodal displacements are equal to the inverse of the stiffness times the forces. And that, ignoring a whole host of details, is simply how FE analysis works. Simple. And from this we find the displacements. Displacements give us strains, strains give us stresses, and the stresses give us forces and moments. Everything derives from the nodal displacements. Now, in the book, I'll then build on from there. So P-delta analysis, which includes the geometric stiffness matrix. Now, this accounts for the way that tensions can increase stiffness and compressions decrease stiffness. Now, you'll note that there can be some forces where the element and geometric stiffnesses cancel out. Now, this will cause the P-delta analysis to fail, or non-convergence. Now, for buckling analysis, we're actually looking for those, and so you can see we've got a lambda times the geometric stiffness matrix. Now, this is a multiplier on the load which causes the collapse, and the deflection, the U, is then the buckling shape. And we use eigenvalue methods to find this. And similarly, we can use eigenvalue methods to take the stiffness and multiply on the mass matrix, the masses of the structure. These will then give us the natural frequencies and also the modal shapes. I also explore various non-linear methods, even down to things like meshless methods, not easy to say, but yeah, time is far too short to look at those at the moment. So you've done the model. Now, what about errors? Never forget errors. Hartford Civic Centre, Schleppner oil rig, CTV building Christchurch. These are just 3 structural collapses that are caused by bad finite element analysis. Thankfully, the first 2 had no casualties, but 150 people died in the 2011 Christchurch earthquake, all in that one building. We might add in the Florida University footbridge to this list, and so on. As I said earlier, all models are wrong, but some are useful. How can you make sure that your models are useful? So FEA, it stands for Finite Element Analysis, but also Finite Element Approximation. No digital computer can exactly represent real numbers. 3.14 is approximately pi. It may or may not be close enough depending on what you're calculating. Now, the maths of FEE is to find a solution to a whole host of simultaneous equations. Now, if we were to find the intersection of 2 lines, then the answer is definite. Add in a 3rd line, and the intersection becomes much more uncertain. So statically indeterminate structures are like this. They have this element of uncertainty about them. So how do we get the best answers from an FE model? There is validation. Validation is ensuring that the model is valid. Does it answer the right question in the right way? Is it realistic? Does it include important checks and details like voids or stability? Is the modeling appropriate? The Harvard Civic Center model was invalid because it ignored important details, such as the way as-built connections induced large amounts of torsion in members which had virtually no torsional capacity. Their analysis approach was also invalid as they did not check for torsional buckling. They did not ask the right questions. The CTV building analysis model was also invalid because they did check for seismic, but they only got center point story drift output. The building had an asymmetric stability system, so torsional drift was significant, and that's what led to collapse. We also have verification, which asks whether the model is giving the correct answers. Does it have errors in it? Now, one of the best ways to verify a model is to have a good idea what the right answers look like. Whether deflection, moment, shear. If the results do not match up with your expectations, then it's because of one of three reasons. 1, your model is wrong. 2, your expectations are wrong. Or 3, the software is wrong. And it is not normally number 3 in commercial software. The most likely answer is either you did not understand the structural behavior correctly or that you made an error in the model. Either way, it's time to dig in and find out where you went wrong. Now, hand calculations, great way to start. Even with a simpler model or assumptions, assume a truss is a beam or a tall building is a cantilever. Use beam theory to get approximate answers. Or make simpler FE models and so on. Now, Schleppner oil rig, that sank because a one-line beam shear force check was never done. So, apart from the errors, approximations inherent in modeling, where do the errors come from? Errors come in units. These are possibly the biggest cause in errors in models, at least the ones that I've seen across on my desk. Confusion between newtons and kilonewtons, or meters and millimeters, whether in the materials, the sections, the model dimensions, the loads. You can quickly find yourself out by a factor of 1,000 or even 1,000,000. If you overstraining the model can cause errors. I remember one case where the engineer put pinned restraints on the ends of all the beams rather than pinned releases. He then complained that the columns had zero load in them. Likewise, lack of restraints can lead to unstable models. Just because you do not have forces in a particular direction does not mean you don't need restraints in that direction. A zero stiffness will always stop the analysis, whether the model is a whole or in an unconnected element. Torsion is often forgotten about, as it sometimes can be crucial. So forgetting was the dominant factor in both the CTV and Harvard Civic Center disasters, amongst others. Inappropriate meshing. That will reduce accuracy, but it can be especially crucial on buckling analysis models, or dynamic models too. Meshing was also a factor in the Schleppner oil rig. Keep halving the mesh until the results stabilize. Second order effects. If you've got large deflections, you need a nonlinear analysis. And then you've got to remember, you cannot multiply or combine results from nonlinear analyses. And there's also whatever else is that you've forgotten. Now, you have your model working well. It is time to make it work even better. Now, optimization is a thing I think that almost all engineers are interested in, whether it's finding the lightest beam to making a bridge, span several kilometers across sea carrying just its own weight. And now we also have the drive towards zero carbon construction, both from industry and from clients. I mean, the construction industry contributes about 8% of the world's greenhouse gases. The main emissions used to be from the service life of the buildings, heating or cooling, but improved insulation and efficiencies like that have greatly reduced those. Now it is the structure which is a major source of of environmental damage, and we need to do our bit by making every building and structure more efficient. Now, I've heard many opinions as to what is optimization, and its simplest term, it is minimizing the cost of something in a design subject to various constraints. Yeah, that the cost, the weight, the amount of material, the construction time, etc., etc. Now, here we have the standard formula, and I'm not quite sure if the standard formula are actually useful, but there seems to be a law that says all text on optimization must include this equation. So here they are. Now, we can put this another way. Optimization is finding the best solution out of the feasible solutions. But it's up to you to decide what the range of possible solutions is. Now, to computerize optimization, you need a cost function, a way of measuring just how optimum or efficient a solution is. And you need to decide on what variables you're going to explore or adjust to find that optimum. And you need to know what is and what is not acceptable. For example, a structure cannot fail, nor can it deflect too much. So you decided you got to minimize the cost or the weight or the structure time anyway, of your structure. How might you go about that? So there are three main categories of optimization. There is the section optimization, determine the best section size. And that is probably the simplest option. It also has the least effect on the overall cost of the building. There is the shape optimization, looks at the shape of the building, of the truss, of the section itself. And then there's the topology optimization, which looks at the scheme as a whole, span directions, number of columns, what materials you're using, and so on. Now, topology has the largest effect on the end result. So this is what you should do first. In fact, this list is actually in reverse order. But topology. So 2012, iStructE President John Nolan gave in his inaugural address, gave us a simple and powerful example of topology optimization. A simple single-story industrial building. Now, if we span the roofs in the short direction, is it best to have 2, 3, 4 bays? If we span the long direction, is it 4 to 9 bays? Do we put columns in everywhere or use hit and miss layout? Do we use moment bases to reduce the frame sizes but increase the cost of the foundations? I mean, even this, we are already dealing with over 100 different layout options. It's worthwhile exploring this, and then this will make big impact on the final structure. Or things like trusses. I mean, I've often wondered about over the years about the various forms of truss and which are the most efficient. Pratt, Warren, Fink, Howe. What I didn't realise was about 100 years ago, an Australian engineer called Mitchell had found the answer, and he used Maxwell's theorem of low paths, and he proved it is possible to determine the most optimum truss. And these are now known as Mitchell trusses, as you see here. And it's true that some have quite a lot of connections in them, which will push up their cost. But this does also mean that you can determine just how close your truss is to absolute optimum. Now, to date, they've been mostly known to a few specialists, tall buildings, that sort of thing. But I would confidently expect that trusses such as one that we see at the top here, we're going to be seeing a lot more of these in future. Now, topology and shape can often get confused. Indeed, the boundaries between the two can be fuzzy. So here are three examples. So here, the original form and the topology remains the same if you can stretch one form into another without breaking it. Hence, the often quoted example that a donut and a coffee mug are topologically the same, which could explain why they go so well together. Now, here the shape is a rectangle or a bowstring, while the topology is the number of internal elements in the truss. Now, shape optimization itself is getting the most from the structure by adjusting the location of the truss nodes, the section corners, the thicknesses, the ridge heights, and so on to get the most efficient structure. I-beams, generally recognized as being very efficient, but still they come in a variety of shapes, depending on whether they are being used for bending or mostly for compression or composite action. And shape optimization is essential if you're designing a compression or tension only structure, as the right shape should minimize the chance of buckling or wrinkles as is appropriate. And we have section optimization, which is something I think all engineers are familiar with, but can still throw up some problems. Optimizing the section for a single statically determinate beam is straightforward, but when the beam stiffnesses interact, then it gets a lot more complex. Even this simple cruciform of two beams, both with the same span, central point load, there are actually 3 principal optimum solutions. I mean, it's actually 4 more, 7 7 total, which I don't have time to cover now. And if you are looking at a more complex structure, such as a two-way spanning veer-and-dahl truss or space frame, then it takes a lot of iterations before you determine what the most effective set of sections are. Now, we do not have time to cover everything regarding optimization now. I've been known to talk about it for several hours, and this book contains 2 chapters on the subject. As a teaser, here is a list of the principal heuristics or methods for optimizing a structure or other engineering problem, all of which we cover. And now we go from looking at state-of-the-art to cutting edge. Artificial intelligence and machine learning. Now, the concept of artificial intelligence has been with us since the dawn of the computer age. The term was invented in 1956 at the Dartmouth Research Project in the US, where a number of element scientists and mathematicians gathered together to make a machine simulate thought. The expectation there was if a carefully selected group of scientists worked together for a summer, then they should make significant progress. Now, 70 years later, we know they were rather optimistic, to say the least. But from a starting point, there were many useful techniques and methods that have arisen, even if none of them have come close to simulating thought. Now, the initial quest for artificial thinking was with symbolic logic or predicate calculus. Now, while they've completely failed to simulate thinking, the natural language processing did give us grammar checkers for our word processors. Very useful. And though by another technique, natural language processing is now found in most homes and pockets. So after machine learning parses speech sounds into words, NLP groups the words into sentences, works out which parts are nouns, verbs, adjectives from the grammatical rules, then determines the instruction or question, and then will either try to find the answer from the internet or play the music of your choice, or do something random. Search routines are AI. It's not possible to directly solve the question, what is the shortest route between 2 points? Instead, AI research produce algorithms such as A star and so on to intelligently search for the shortest route with a mixture of estimates, calculation, and data storage. Likewise, searching through unsorted databases is also an AI application, the most famous of which has become a verb, to Google. Another aim of AI is to encapsulate knowledge and enable automatic decision making, and this can be in the form of a state search. So state search builds a tree of possible decisions and then navigates it to find the best possible answer, or at least the most promising route to the answer. And these have proved very successful in games. Games like chess are formal, they have rules, and are boundaries. And while neural networks have been around since the 1960s, they were initially very unsuccessful. But now, with fast processors, powerful training algorithms, and the huge amount of data available on the internet, they are now the dominant machine learning method. Neural networks are inspired by how neurons in the brain connect together, collating data to enable pattern recognition. Artificial neural networks work by taking numerical data with a number of inputs, multiplying them, adding these together multiple times until an output indicates which is probably the answer. If they are right, those options are strengthened, and if they're wrong, they're weakened. And this neural network is then trained over thousands of iterations until it consistently, or at least generally, gives the right answers. Now, while machine learning methods such as deep learning have proved successful in applications such as recognizing videos of kittens on YouTube, in structural engineering, we have the problem of a lack of suitable data to train the systems. Hopefully this will change in future, and we will see more AI and machine learning engineering assistance in future helping us in our tasks. Now, computing has already made changes to the industry in my lifetime, and I foresee more of them coming. AI and machine learning will increase their presence. I think the major change to us will be due to climate change and the efforts to mitigate it. So the main thing that we must change is how much material we build. We must use less. We must also build less and refurbish more. Only doing new builds when there's not an option. Optimization is going to be a significant tool for us in the future, whether automatically exploring the structural topology, shape or sections. And I know there's a fear that optimization could reduce factor safety, but I think hopefully we can see that improving topology and shape of the structures will improve efficiency without compromising any safety. There's also concern it might increase costs, which, yeah, in some circumstances it might be true, but by no means all. More efficient construction should be cheaper. There are also increased number of clients who want to ensure their projects are environmentally sound. And on the plus side, reducing the cost of structures will also mean more efforts, so should mean more fees. Similarly, refurbishment of structures requires back analysis of existing structures to work out what's actually there, and the searching for what is actually built from readings is another topic in computing. There are other technology advances we don't have time to discuss now. Mobile computing, it is there, it will increase its impact. I think many engineers over the last year without laptops and mobile phones will have really struggled to keep their businesses going. And also enabling me to talk to you half a world away. Cloud computing will reduce the need for local high-spec hardware, yeah, including more mobile computing. And then there's quantum computing, which promises much. We don't know yet whether it can deliver it or not, but quantum computing is far too weird to explore now at the end of this talk, but does get a section in the final chapter. So as I mentioned, I cover all these topics and more in computational engineering, and I'm very grateful that it has been very well received and attracted amazing reviews from around the world.